Good morning, respected sir and ma'am. My name is Pujita Krishnan, and I am here pursuing my first year in Electronics and Communication Department, Section B from Institute of Aeronautical Engineering. My roll number is 21951 A0477. Well, here I would like to present my linear algebra and calculus presentation on the topic generalized Cayley-Hamilton theorem. So before getting into this topic, I would really like to thank my department for giving me this great opportunity as it helped me in getting a new experience and gaining more knowledge about the topic, which is already a part of my second module syllabus. It was indeed a very interesting topic to learn about and know about how the theorem got derived by the two great mathematicians, Arthur Cayley and Sir William Rowan Hamilton. So let's get on to our presentation. Firstly, I would like to begin by outlining about the overview, which is about Arthur Cayley. The other topic is about Sir William Rowan Hamilton, Cayley-Hamilton theorem and its derivation, a direct algebraic proof. Why is Cayley-Hamilton theorem useful for? Uses of Cayley-Hamilton theorem in our daily life and two example problems. So let's start with our presentation now. About Arthur Cayley. Arthur Cayley, who has lived in the period of 16th August 1821 to 26 January 1895, was a prolific British mathematician who worked mostly on algebra. He helped found the modern British school of pure mathematics. As a child, Cayley enjoyed solving complex maths problems for amusement. He entered Trinity College, Cambridge University, where he excelled in Greek, French, German, and Italian, as well as mathematics. He worked as a lawyer for 14 years. He postulated the Cayley-Hamilton theorem that every square matrix is a root of its own characteristic polynomial and verified it for matrices of order 2 and 3. He was the first to define the concept of a group in the modern way. As a set with a binary operation satisfying certain laws, formally, when mathematicians spoke of groups, they had meant permutation groups. Cayley-Hamilton and Cayley tables and Cayley graphs, as well as Cayley's theorem, are named in honor of Cayley. So this is all about our great mathematician Arthur Cayley, who was a part of this finding Cayley-Hamilton theorem. Coming to our next great mathematician, who was Sir William Rowan at Hamilton. He was the other one who had helped Cayley to finding the Cayley-Hamilton theorem. Sir William Rowan Hamilton lived in the period of 4th August 1805 to 2nd September 1865. He was an Irish mathematician, Andrews Professor of Astronomy at Trinity College, Dublin, and Royal Astronomer of Ireland at Dunsink Observatory. He made major contributions to optics, classical mechanics, and abstract algebra. His works was of importance to theoretical physics, particularly his reformation of Newtonian mechanics, now called as Hamiltonian mechanics. It is now central both to electromagnetism and to quantum mechanics. In pure mathematics, he is best known as the inventor of quaternions. Hamilton is said to have shown immense talent at a very early age. He was a very talented person. And Hamilton's predecessor as Royal Astronomer of Ireland and later Bishop of Cloyne, Dr. John Brinkley remarked of the 18-year-old Hamilton. This young man, I do not say will be, but is the first mathematician of his age, and that is all is about the great mathematician of Sir William Rowan Hamilton. Moving on to our next slide, Cayley-Hamilton theorem. So, what is Cayley-Hamilton theorem? In linear algebra, the Cayley-Hamilton theorem, named after mathematicians Arthur Cayley and William Rowan Hamilton, states that every square matrix over a commutative ring, such as the real or complex field, satisfies its own characteristic equation. If A is given n cross n matrix and In is the n into n identity matrix, then the characteristic polynomial of A is defined as P of A lambda equal to det of lambda In minus A, where det is the determinant operation and lambda is the variable for scalar element of the base ring. Since the entries of the matrix lambda In minus A are linear or constant polynomials in lambda, the determinant is also an nth order monic polynomial in lambda. The Cayley-Hamilton theorem states that this polynomial expression is equal to the zero matrix, which is to say that P of A equal to 0. It has been extended to rectangular matrices, block matrices, pair of commuting matrices, and standard and singular two-dimensional linear systems. The Cayley-Hamilton theorem has been extended even to n-dimensional systems and to continuous discrete time linear systems. This is about our Cayley-Hamilton theorem. This is the continuation of Cayley-Hamilton theorem, which states, what is Cayley-Hamilton theorem? It states about that a square n by n matrix A satisfies its own characteristic equation. Thus, we can express A power n in terms of a finite set of lower powers of A. This fact leads to a simple way of calculating the value of a function evaluated at the matrix A is f of lambda equal to A, which is lambda power n plus A1 lambda power n minus 1 plus A2 lambda power n minus 2 plus so on and so forth plus A suffix n minus 1 lambda plus an equal to 0, where I is the nth order unit matrix and 0 is the nth order zero matrix. This is Cayley-Hamilton theorem derivation part, like how we got the A minus lambda I, that derivation. This is, we have to put lambda equal to A. Then we will, after substituting lambda equal to A, we will find minus 1 power n, capital A power n plus A1, capital A power n minus 1 plus A2, capital A power n minus 2 plus so on up to A nth I equal to 0, which this is what implies that A satisfies its own characteristic equation. So this is kind of proof to make us know how we got A minus lambda I equal to 0. The next topic is about a direct algebraic proof to this theorem, to support this theorem. So moving on to this topic, we this proof is used just the kind of objects needed to formulate the Cayley-Hamilton theorem. Matrices with polynomials as entries. The matrix T in A, whose determinant is the characteristic polynomial of A, is such a matrix, and since polynomials form a commutative ring, it has an adjunct B equal to adjoint of Tin minus A. Then, according to the right-hand fundamental relation of the adjunct, one has Tin minus A B into B equal to det Tin minus A bracket close In equal to Pt It. Since B is also a matrix with polynomials in T as entries, one can, for each I, collect the coefficients of T in each entry to form a matrix B of numbers, such that one has this thing, which while this looks like a polynomial with matrices as coefficients, we shall not consider such a notion. Write a matrix with polynomial entries as a linear combination of n constant matrices, and the coefficient t has been written to the left of the matrix to stress this point of view. So this is about the proof of the Cayley-Hamilton theorem. Let us look at a small example of the Cayley-Hamilton theorem. We saw that matrix M, which is a 2 by 2 matrix, which is of 1, 1, minus 2, 4, has characteristic equation of lambda square minus 5 lambda plus 6 equal to 0. So, m square equal to our m into m matrix, which gives us, after multiplication of these two matrices, we get minus 1, 5, minus 10, 14. If we substitute m in the place of lambda over here, we get m square minus 5m plus 6i. I stands for identity matrix. So after substituting the values of m square, we get this value over here, minus 5m. M is this matrix which is actually given to us already. So that one, and identity matrix of a 2 by 2 matrix is 1, 0, 0, 1. After simplification of all of this, we get a null matrix, which is 0. This illustrates that Cayley-Hamilton theorem is a square matrix satisfies with its own characteristic equation. Coming to the next slide, it's a very interesting topic. You all wonder where is Cayley-Hamilton theorem useful, and what is it useful to find? So let's get on to this. Cayley-Hamilton theorem, it is useful to find the inverse and power of a matrix. Just like I have shown in these two pictures, it is useful to find the matrix over here, power of the matrix over here, and here it's useful to find the inverse of the matrix, of the given matrix, and also it is useful to find only inverse of the matrix. And the third one is it is also useful to find only power of a matrix. So these are the three things which Cayley-Hamilton is useful to find for. Moving on to our next slide. So all of you ever wonder why this Cayley-Hamilton theorem is useful in our day-to-day life. So let's get to know about this. Matrices are used in many fields like robotics, automation, encryption, quantum mechanics, electrical circuits, 3D visualization, in 2D, etc. In 2D visualization as well as 3D visualization. all places we require the power of the matrix or the inverse of the matrix. So it is useful in these all kind of things. Cayley-Hamilton's theorem helps in expressing the inverse as a polynomial expression of the matrix, higher powers of the matrix in terms of the lower parts of the matrix. The Cayley-Hamilton theorem and its generalizations have been used in control systems, electrical circuits, systems with delays, singular systems, especially and in DC circuits too. Let's get on to this slide and know a problem based on Cayley-Hamilton theorem. Let's solve it. This is the example 1 wherein the question is verify Cayley-Hamilton theorem for the matrix A equal to, which is 3 by 3 matrix, 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Hence compute A inverse. This is the question given to us. So let's solve it now. The characteristic equation of A is A minus lambda I equal to 0, wherein we have to subtract by lambda in the principal diagonal elements. We get 2 minus lambda minus 1 1 minus 1 2 minus lambda minus 1 1 minus 1 2 minus lambda. The whole is in the det equal to 0. On simplification of this, we get lambda cube minus 6 lambda square plus 9 lambda minus 4, which is equal to 0. To verify Cayley-Hamilton theorem, we have to show that A cube minus 6a square plus 9a minus 4i equal to 0. We just have to substitute a in the place of this lambda. After substituting, we get the next equation, which is the first equation over here. Now we have to do a square. In order to find a cube, we have to first start with a square. The matrix which is given to us is multiplied to each other, square matrix, and then it's a 3 by 3 matrix which is multiplied together, and by which we get 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6. This is the answer of the a square. After finding a square, we multiply a square again into the A matrix, again multiplied by the A matrix. After multiplying a square by A matrix, we get 22 minus 22 minus 21 minus 21 22 minus 21 21 minus 21 22. This is what we get as A cube. So substitute its value in this place. Moving on to the next slide, we get A cube is 22 minus 22 minus 21 minus 21 22 minus 21 21 minus 21 22 minus 6 into a square. A square is this, which we already found here in our first step. We just have to substitute this box over here plus 9 into A matrix. This is the A matrix minus 4 into I, which is the identity matrix. After substituting the values, we get 0, 0, 0, 0, 0, 0, 0, 0, 0, which is equal to 0. So after getting the null matrix, this indeed verifies our Cayley-Hamilton theorem. Now, pre-multiplying, we have to find the other part of the question, which is about compute A inverse. So in order to find our A inverse, we do pre-multiplying both sides of equation 1, which is here, this equation 1, we multiply this by A inverse. After multiplying both sides by A inverse, we get 4A inverse, which is equal to A square minus 6A plus 9I. We just took this 4A inverse to the right side and the rest is on the left side. So after getting 4A inverse, we just have to find on simplification, we get 4A inverse, which is equal to 3, 1, minus 1, 1, 3, 1, minus 1, 1, 3. This matrix we get after substituting all the values in this equation, in the above equation. After substituting all the RHS side, we get 4A inverse value matrix, which is this. And after getting this, we take A inverse, which is the given matrix, by 4. We take the 4 to the right side and divide it, by which we get 1 by 4, 3, 1, minus 1, 1, 3, 3, minus 1, 1, 3. So this is what is our A inverse. It's very easy problem, but very interesting problem at the same time. Let's go on to our second example, which is given A equal to 3 by 3 matrix, which is 1, 2, minus 1, 0, 1, minus 1, 3, minus 1, 1. Find adjoint A by using Cayley-Hamilton theorem. So this is the question given to us right now. Let's solve it. The characteristic equation of the given matrix A is that of A minus lambda I equal to 0. This is the formula of the characteristic equation. So let's substitute it and proceed. We have to subtract minus lambda from the principal diagonal elements. So let's move forward. 1 minus lambda, 2 minus 1, 0, 1 minus lambda, minus 1, 3 minus 1, 1 minus lambda, of that equal to 0. On simplification of this whole matrix, we get the equation as lambda cube minus 3 lambda square plus 5 lambda plus 3 equal to 0. Let's proceed. By Cayley-Hamilton theorem, A should satisfy, by which we just substitute A in this equation in the place of lambda. Then we get A cube minus 3A square plus 5A plus 3I equal to 0. By pre-multiplying A inverse on both sides, we get A square minus 3A plus 5I plus 3A inverse, which is equal to 0. Because 0 multiplied by anything is equal to 0. But A inverse, if you multiply, we get after multiplying, we get this equation. Let's find out what is A inverse. A inverse, firstly, after knowing what is A inverse equal to minus 1 by 3 equal to A square, minus 1 by 3 into A square minus 3A plus 5I, which is a first equation. We get this equation by moving all the elements or all the numbers to the right hand side and keeping 3A inverse on the left hand side. After getting the equation, send the 3 to the right hand side, which divides the whole equation, and which due to which we get this equation. So now we have to substitute the values in order to find the matrix. A square is the given A matrix should be multiplied with again A matrix, by which we get A square equal to minus 2, 5, minus 4, minus 3, 2, minus 2, 6, 4, minus 1. And this is the matrix of A square matrix. What is 3A? 3A equal to multiplying 3 into A matrix. We get 3, 6, minus 3, 0, 3, minus 3, 9, minus 3, 3. This is what we get in as 3A. From first equation, which is this, we get minus, after substituting all the values, we get minus 1 by 3 equal into minus 2, 5, minus 4, minus 3, 2, minus 2, 6, 4, minus 1, minus into other box 3, 6, minus 3, 0, 3, minus 3, 9, minus 3, 3. And plus, after substituting this in 5 into identity matrix, we get 5, 0, 0, 0, 5, 0, 0, 0, 5. After substituting all the values, we get minus 1 by 3 into 0, minus 1, minus 1, minus 3, 4, 1, minus 3, 7, 1. And we know that A inverse equal to adjoint A by mod A. Adjoint A by det A. Adjoint A equal to A inverse det A. Let's proceed. So det A we get as, after simplification and all, substituting the values in this formula, we get det A equal to 1, 2, minus 1, 0, 1, minus 1, 3, minus 1, 1. But after doing the det of this matrix, after on simplification of this matrix, we get minus 3 as an answer of det A. So adjoint A equal to minus 3, which is det A, is already given in this formula, A, and then multiply it with this minus 1 by 3, and this 0, minus 1, minus 1, minus 3, 4, 1, minus 3, 7, 1. After multiplying A inverse into det A, we get this as our adjoint A matrix. 0, minus 1, minus 1, minus 3, 4, 1, minus 3, 7, 1. This is our adjoint A matrix. Thank you. That's the end of my presentation. I would like to end this over here and get a positive response from your side, sir, as your feedback matters a lot to me to get much better and do it much better than this next time. Thank you, sir.